Welcome everyone. We're now going to have a few science presentations for you on specific research activities within each RC. To get us started, we have Iman Marvian, one of my colleagues here at Duke in the ECE department. And he'll be talking about something that Ken mentioned in his overview, looking at these learning of multi-qubit interactions in the presence of symmetries. So I know we have lots of students and postdocs in the audience, so I encourage y'all to ask questions and speak up. This is a friendly workshop, despite others' best efforts. So please feel free to participate. You're great, Ken. Don't worry. Okay.
Thank you, Crystal, for the introduction. Welcome, everyone, to Duke. If this is the first time at Duke, please make sure to see, the campus. It's a very nice campus. See our chapel and also Duke Garden, which is very close, 5 minutes walk from here. So in this talk, I'm going to present two recent results on both learning and synthesizing multi-qubit interactions. So by multi-qubit interactions, I mean Hamiltonians like Z tensor n copies of Z, which simultaneously couples n qubits together, or for example, contour Z with arbitrary number of contour qubits. This type of gates have broad applications in quantum simulation, for example, in the context of simulating gauge theories or simulating a fermionic system when you do your Jordan-Wigner transformation or Browicki type transformation, and other areas like quantum error correction. And one common theme in this talk, maybe not surprisingly, will be symmetries. So symmetries, of course, always have some implications that we all like conservation laws, decomposition to irreducible representations, all those standard techniques and implications. But what I want to emphasize in both projects that I discuss in this talk is that symmetries sometimes have some unexpected implications, some impose some unexpected constraints, but they also bring some unexpected possibilities and opportunities. And when I talk about symmetries, I mean symmetries in a very broad sense. It could be symmetries of the system that you are trying to simulate. It could be the symmetries of fundamental symmetries of nature, or it could be symmetries of the native interaction on your quantum computer, for example, symmetries of your Jaynes-Cumming interaction. Or, sometimes you impose symmetries yourself to suppress certain errors. Or, another example that you will see in this talk will be the case where you impose symmetries to simplify the optimal contour problem, because now you can reduce the number of parameters that you need to optimize over them. By the way, feel free to interrupt and ask questions whenever there's questions. So this talk, as I mentioned, there are two parts. The part one is about efficient learning and verification of multi-qubit interactions, and in the presence of symmetries. So this is a work that is done, an experiment that has been done here at Duke Quantum Center by Chris Monroe's group. Most of the work is done by Mila Zhukas, who was sitting here somewhere before. Yes, she's there. Ask all your questions from her. And Qingfeng Wang and Orkatz, Chris Monroe, and myself. So this will be part one of my talk about verifying and learning n-body interactions. The second part is just very, very fresh result. This is just posted last night on arXiv, and well, it should show up tonight on arXiv. We don't have the arXiv number yet. It's about implementing permutation and invariant n-body gates with Tavis-Cummings interaction. So Tavis-Cummings interaction is essentially Jaynes-Cumming interaction that we can realize on trapped ion quantum computers with permutational symmetry, when all your qubits have identical coupling to the harmonic oscillator. Okay, so let's start with the first part, which is efficient learning of n-body interactions. So here we start with a very simple question. The question is, do dynamics under three-body interactions, or more generally k-body interactions, have any signature which make them distinct from two-body interactions, so that we can look for that signature and efficiently verify them, or maybe not efficiently. Let's not even worry about efficiency. Can we directly focus on three-body and filter out the effects of two-body and detect the presence of a three-body interaction? So let's try to formulate. There are different ways to formulate these questions. So the simplest formulation is, let's say I have a black box. It's a unitary process. It contains some two-body gates, two-qubit gates, that I have no prior information about them. And then there is a hypothetical three-body gate also, like e to the I alpha 3 z tensor tree. And the goal is to obtain information about this hypothetical three-body gate, or in other words, obtain information of a tree. We want to verify, is that this three-body gate is there or not? So we can also formulate this problem in terms of Hamiltonians. So suppose I have a time-dependent Hamiltonian from some time 0 to a fixed time t. This Hamiltonian contains some two-body terms, here h2t, and some hypothetical three-body interactions. And then the goal is, again, to prepare this system in arbitrary initial states and perform arbitrary final measurements and verify or test the presence of this hypothetical three-body interactions in this dynamic. Okay? And so the question is this possible or not? Now, it turns out that this is a kind of old question. It has been studied a long time ago, 30 years ago, and David DiVincenzo answered this question for us. David DiVincenzo tells us that two-qubit gates are universal. You can realize any unitary transformation with two-qubit gates. So there's no way for you to, if you don't have any prior information about those two-qubit gates, there's no way, it's impossible to detect the presence of these three-body interactions. Okay? So now what we have shown in this recent work, in this recent experiment, that if you have a global symmetry, a global U1 symmetry, for example, symmetry under rotations around the z-axis, then not only this becomes possible, but you can also do it efficiently. So in this context, for example, we can detect the presence of this three-body gate here. I want to emphasize that this three-body gate is not breaking that symmetry. So we are not trying to look for, trace of symmetry breaking. It's still respecting that symmetry, and yet we can detect it, and we can essentially, and in the presence of unknown two-qubit gates. Okay? So we introduced this quantity that I will define it later. Delta 3 is a phase between 0 to 2 pi. And we claim, when we show experimentally, that in this quantity, this phase is insensitive to the presence of two-body interactions in the presence of a symmetry. So it somehow filters out the effect of all these two-body gates and focus on this phase alpha 3. Essentially, we prove this relation. Delta 3 is equal to minus 8 alpha 3 in this example that I have here. There's more broader analysis in the paper and other examples and other settings. But in this simple example, delta 3 will be minus 8 alpha 3. So it filters out the effect of two local U1 invariant unitaries, and maybe even more importantly, it can be measured efficiently. In particular, you can just measure it by focusing on a subspace of this exponentially large Hilbert space, which grows linearly with the number of qubits. It's linear in n. So Mila and her collaborators did the experiment. So this is an example of unitary transformation that they realized on trapped ions. And so this circuit, for example, has blue two-body gates, two-qubit gates, that are U1 invariant, meaning that they are commute with the action of rotation around Z. And the point is, we have only this three-body interactions, and we can directly observe the effect of this three-body interaction without knowing anything about these two-qubit gates. So she measures this quantity delta 3 and observe this, nice plot that agrees with our theoretical prediction. Delta 3 should be minus 8 alpha 3. So we expect this 8, periodicity essentially. And the point is, we also verify that as we change the values of these two-qubit gates, because as long as they respect the U1 symmetry, then this quantity doesn't care. It just filters out their effect. Okay? So now, in the next few slides, I have to tell you what is this quantity delta 3. I have to, tell you a little bit about the background of this work. And also, in the paper, we explain how this can be generalized to K-body. So the background of this work goes back to a no-go theorem. So usually no-go theorems maybe do not have direct implications. In this case, this no-go theorem has a direct implication, which is this experiment. So the no-go theorem says, in the presence of symmetries, essentially the universality result of DiVincenzo doesn't hold in the following sense. If you want to implement an arbitrary unitary that respects a symmetry, for example, a global U1 symmetry, you cannot decompose it to a sequence of two-qubit gates that respect the same symmetry. Okay? So in this sense, that universality result fails, not necessarily in the computational sense, by the way. So I usually use this torus. I will come back to this torus and define precisely what do I mean here. But this torus essentially is representing the group of all unitaries that respect the symmetry. And then you have this helix that goes a finite number of times around this torus. And this is a subgroup that are realizable, for example, by 2-qubit gates. And the point is, this torus doesn't go around this helix doesn't go around the torus forever. Otherwise, if it wraps around this forever, it can get arbitrarily close to any point on this torus, and then experimentally, these two become indistinguishable from each other. The fact that you cannot, in other words, if it wraps around the torus forever, you can get arbitrarily close. Even though you cannot implement your desired unitary, you can get arbitrarily close to it. Mathematically, this means that the subgroup is a compact Lie subgroup of the group of all unitaries that respect the symmetry. Now, let's look at this symmetry more precisely. So here I'm talking about global rotation around Z. So unitaries that respect this unitary commutes with sum of Pauli Z operators, which means that they are block diagonal with respect to sectors with different excitation numbers or Hamming weights, depending on the eigenvalues of sum of Z, which is the number of ones essentially. And so general unitaries that respect the symmetry are in this form. But it turns out that if you ask what is the dimension of the torus here and the dimension of the helix, the difference between the dimension of torus and helix will be n minus k. Again, this notation VU1 and k is the group generated by the k local U1 invariant. And this other one, this bigger one, is the group of all unitaries that respect the symmetry. And the point is the difference of their dimension is n minus k. Now, to do experiments, to observe this phenomenon, we need to understand what are these constraints better. And please bear with me. I have one slide with some math, but I need to explain what are the nature of these constraints. But roughly speaking, the nature of the constraints in the case of group U1 is only constraints on the relative phases between sectors with different Hamming weight or different number of excitations, right? Only you are constraining the relative phases that you can create between these different sectors. It turns out that for other groups, you can ask similar questions, like for example, for SU2, SU3. And for some groups, there are much more complex type of restrictions. For example, for SU3, sometimes you see, the unitary that you perform in this sector uniquely determines the unitary that you can perform in this sector. There will be correlation between different sectors. That doesn't happen in the case of group U1, but still there are some interesting constraints. And so I want to explain exactly what are those constraints. So this is my one mathematical slide. So I said that my unitaries are block diagonal. And so now each of these VMs are unitary that you realize in one particular block, for example, block with M excitations. And then you can think about to formulate the idea of relative phases between sectors with different Hamming weights, for example. You can think about the determinant of these unitaries. Because these are unitaries, the determinant will be a phase. So theta m will be the determinant, essentially that phase associated to VM. And these phases, because they are periodic, they define a torus. So the torus that I mentioned before is exactly defined by this phases of determinants of unitaries in different sectors. And now the point is, if you have Z, for example, interaction Z or Z tensor 2 or Z tensor 3, each of them give you a direction to move on this torus. And as you have more and more interactions, if I have two-body interactions, I can move only in this direction. If I have three-body interactions, now I can also move in this direction. And so by probing which directions on this torus I can move on, and where I am on this torus, essentially, I can detect whether I have two-body interactions or three-body interactions, etc. Just think about the simplest example of this. Let's say I have just one qubit. There is no notion of locality, but it's still interesting to think about this. So the group of unitaries that respect the symmetry are all unitaries that are diagonal in the computational basis. It's the simplest story. So you have just two phases, theta 0 and theta 1. In this case, I have a 2D torus. And then on this 2D torus, theta 0 and theta 1, neither of these phases, by the way, are physically observable. We cannot measure them in the lab because they are not invariant under a global phase change. If you multiply my unitary with a global phase alpha, for example, all these phases will change. So I cannot measure them. But still, I can now define two axes here, theta 0 plus theta 1 and theta 0 minus theta 1. Theta 0 plus theta 1 is sensitive to this global phase change. It's essentially, you can argue that it's realized by zero-body interaction, which is essentially the identity gate. Whereas theta 0 minus theta 1 is now insensitive to this global phase change, and it's realized by one-body interaction, which is Z. Okay? Now we can generalize this idea exactly to n-body interactions and try to detect L-body interactions. The point is I want to think about the linear combination of these thetas with certain coefficient CLM. So remember, thetas are all the phases on this, the phases of the determinant of these unitaries. And I want to combine them with some integers, look at some linear combination of them with some integers. Why this should be integer, by the way? Why CLM should be integer? Because theta m's are defined only mod 2 pi, and therefore, if you want to have a continuous way of labeling your qubits or characterizing your qubits, you can only combine them with integers. Anyway, so this is a work that is previously presented here in this paper from 2022. The point is, these quantities that you can define in this way allow you to perfectly distinguish between, for example, 2-body versus 3-body versus 5-body. They can zoom on this particular direction, and or they are only sensitive. For example, phi L is only sensitive to L body. Question?
Yeah. So just to get like an intuition for it. So under the U1 restriction, say I'm picturing this as like my U1 symmetry here is corresponding to my particle number conservation. So if I have some initial number of particles distributed through my system, and I do interactions locally which conserve the particle number, I can't reach some arbitrary configuration of the particles. And I guess that like, if I start in a single charge sector, then I wouldn't see this effect, right? Like I have to start in a superposition of charge sectors.
You don't see it for, exactly, you don't see it for U1. But for example, you'll see it for SU3. So it depends really to the group. For U1, you don't see it.
But in U1 too, like don't you still have this restriction that you can't realize like all global U1s from like local U1s? Like if I start in like a superposition of various charge sectors, and I only have the local restrictions, are there certain like superpositions with certain phases I can't reach? Or
so you cannot go from a general density operator to a general density operator using, there are still restrictions, but you need to have superposition between different sectors. If you are restricted to one sector, you won't see it. You will see it, for example, for SU3, but not for U1. Thanks for the good question. Any other questions? Okay. Now, I mean, this was, my only, more mathematical slide. So the point I wanted to make here is that by looking at this, these phases, essentially, the phases of the unitaries that you realize, and by phases, I just really mean the determinant of those unitaries, you can detect the locality of the interactions. Okay? But the problem with this approach is that it requires essentially full tomography, because you need to know what are the unitaries that you realize in each sectors. And what we achieved in this recent work with Mila and others, so is that we find a way to avoid full tomography. We can do it efficiently, essentially. And what is the idea? There's a trade-off here. The point is, let's say the idea is essentially we want to settle for a weaker goal. The weaker goal is maybe I don't need to distinguish between, for example, 3-body interactions and 5-body interactions and 7-body interactions. I'm just happy to distinguish between all of them and 2 local ones, like Z2 and Z tensor 2 or Z or identity. Okay? If I settle for this weaker goal, that I want to filter out only 2-body interactions, and then I don't care about distinguishing between Z tensor 3 and Z tensor 5, for example, then you can do it much more efficiently. And this quantity that I mentioned before, delta 3, is exactly achieving that. So this is essentially, so using that notation or that concept that I defined before, thetas are the phases of determinants of unitaries that you realize in different sectors. And the point is, I only need to look at these 4 particular sectors. Theta sector with n-1 excitation, n-1 number of 1s and just 1 0. 1 excitation, which is 1 qubit in a state 1 and all the others in a state 0. Theta n, which is all of them in 1 and the rest in 0, and theta 0, which is all of them are in a state 0. If I only know the thetas for these 4 sectors, then I can calculate this quantity, and I can, you can then prove that delta 3 will filter out the effect of all 2-body interactions. Okay? And again, the point is, as opposed to those phi L quantities that I defined before, this quantity can be measured efficiently because the subspace that I need to care about, this is an n-dimensional. Theta 1 is defined as n-dimensional because these are sectors with hang width 1, sectors with hang width n-1. They are both n-dimensional. And then you have these sectors with theta n and theta 0, which is all 1-dimensional. So the relevant subspace that I need to probe is just 2 times n plus 1, 2 times n plus 2 dimensional. Okay? I don't need to care about the rest of the Hilbert space. Just by looking to this subspace, I can detect the presence of 3-body interactions, essentially. Or, to be more precise, I can filter out the effect of 2-body interactions and see whether there's anything left over, like 3-body or 5-body. Okay, and so this is what Mila and others did in the experiment. So they measured, essentially, this relation between these phases. And, for example, to measure theta n minus theta 0, they use GHZ state. This is maybe a new way of using GHZ state for metrology, so to detect n-body interactions, essentially. And by combining them, essentially, they could calculate the value of delta 3, and they could check this identity, delta 3 equal to minus 8 alpha 3. Okay? So they also managed to measure L-body phases, even though it requires full tomography. And check that whether they are insensitive to 2-body interactions, etc. Okay, so this is the end of the first part of my talk, which was about detecting L-body, detecting M-body interactions. If there are questions about this, I can pause here and.
Yeah, so going back to actually Ken's question at the beginning about RC1.
Yes.
So if, let's say, I measured a 3-body interaction, how can we tell for sure it's not, that one is not introduced by noise or errors in your machine? Rather than there's actually something happened, indeed a 3-body interaction.
Yeah, that's a good question. I mean, there are relations that you can verify. So, for example, by this measurement that you do, you can check whether these phases, they should satisfy certain relation among them, right? And that gives you some information about, for example, let's say in this case, because I'm assuming that I have a U1 symmetry in my Hamiltonian that I'm simulating or Hamiltonian that I'm realizing. If there's a noise that breaks this, I can detect it. If I start with a state that has Hamming weight 1 or superposition of states with Hamming weight 1, and then I run this process, and then I detect something with Hamming weight 2, I know that there is an error here. So that's actually a mechanism built in this process that allows me to detect errors. Yeah, but that's a good question. Other questions? Go ahead.
So you talked about a list of different scenarios where a system can have symmetry. Like, is there, like, how should I think of the result presented? Like, what would be the context where this setup would be most relevant, either for like detecting symmetry in like that naturally arise or synthetic? And also, like, I guess something that I'm missing is that the circuit was still, at some point, you need to break the symmetry to prepare the GHZ state, and I assume also to do the detection. And I guess the 3-body interaction, is that inherent in the physical system, or is that actually?
Yeah, these are all lots of good questions. So in this paper, I show, so this question, for example, whether do you need to break the symmetry or not? So for this detection process, I show that actually you don't, if you allow me to use an ancillary system. This is an idea that people have previously used, for example, in metrology, quantum reference frame, that instead of using GHZ, you can essentially create an entangled state that has a fixed number of excitations. It's an eigenstate of sum of all Z's, okay? And then that state still can do whatever you want to do with your GHZ state. So you don't need, but in the experiment, just for experimental limitations, we avoided that. So that's a good question. So because at least especially in the initial work, there are two essentially areas that you can think about applying this. One is probing fundamental interactions in nature. The second is, now let's say you have a quantum simulator. It's supposed to implement this complex Hamiltonian evolution, and you want to just verify it efficiently, that whether it has those claimed, for example, 3-body or 4-body interactions. The claim is, and we are always looking for different ways of, without opening all the details and without following all the steps in this, just look at the end and follow for some signatures that allows us, check for some signatures that allows us to obtain information about the process in the black box. So that's one. So if your simulator is claiming that I am implementing these m-body interactions for you, to simulate your gauge field theory, then you can just use this and probe that effect without really opening all the steps in this. But these are good questions. Thank you. Maybe let me go with this and then come back to those questions. There are 2 more questions. I promise to come back to that. Okay. So second part. This is fresh. Was posted last night by Plato and myself. Plato is sitting there at the back of the room. And in this work, at RQS Institute, we all love and learn about trapped ions, despite Ken's complaints. No, Ken's actually convinced us to learn about trapped ions. And so one question that you can ask in that context is, what you can do if you don't have individual control over single qubits? Okay? Suppose I want to apply a global field, global beam, that hits all the qubits in the system uniformly, and I don't want to go through the trouble of having individual control. Now, I mean, you may say, I have individual control, why you're worried about that? So the point is, here we are exploiting whether you can do certain gates in this way even simpler or even more efficiently. And this will simplify, as I will explain, our analysis of optimal control. Anyway, so what do I mean by this global fields that affects all qubits uniformly? And in other words, they are permutation invariant. We have, of course, our single qubit X gate or Z fields and X field, which is just uniform X and uniform Z. But we also have Jane's coming, which when you have couplings with all of these qubits are coupled identically or uniformly to your harmonic oscillator, is called usually Tavis Cummings Hamiltonian, and that's it. So I want to just see with these 3 Hamiltonians what type of unitary transformations I can realize on my qubits. And in particular, can I realize n-body Hamiltonian Z tensor N, or can I realize, for example, control Z or not? And you would say, why not? I mean, these guys have permutational symmetry also, and I'm using Hamiltonians that have permutational symmetry. Why not? The problem is, I mean, after that going through the experience of working with that Nogo theorem, now I'm very, very suspicious about any intuition that I have about these things. I know that it's highly wrong, so I need a proof. So we went through this process, and we proved this result, that if you only have these 3 Hamiltonians, which are all permutation invariant, by coupling your qubits to a harmonic oscillator, you can realize all permutation invariant unitaries, including the examples that I showed you before. Harmonic oscillator here is initially prepared in a state in the vacuum, and this unitary V is a unitary transformation that couples my qubit to harmonic oscillator, and the overall effect on the qubits will be this permutation invariant unitary U, which can be arbitrary. Okay, I can realize this case that I mentioned before. So, and one corollary of this result is that you can prepare an arbitrary entangled states in the symmetric subspace just using these 3. That includes, for example, GHC, DKS states, and etc. Now, these are some formal theorems. Ken usually doesn't care about my formal theorems, so I just want to show him that we also have some actual things that could be practically useful. So we say 2-qubit case, permutation invariant 2-qubit case. There are a lot of interesting 2-qubit cases, such as control Z, swap, I swap, square root of I swap, and then we found optimal or close to optimal implementation of those gates. Some of these gates, again, you may say, I don't care about your permutational symmetry, but some of these gates might be even faster than the gates that you usually realize with, by breaking permutational symmetry. For example, the swap gates looks to be very fast, seems to be very fast. Now, this is a problem that we need to study next, like compare these implementations with what you can do, for example, with Morvan-Sorenson or other approaches, or Chirac-Zoller. So we found also some useful gadgets for implementing these 2-qubit gates. For example, this gate that we call it F gate that swaps essentially two excitations from qubits with excitations in the oscillator. And using this gate, we built many other gates, essentially. We designed, essentially, we found a gate for swapping the state in the symmetric subspace of qubits. So in n qubits, I have n plus 1 dimensional subspace of symmetric states. And we swap this with the subspace of, states of harmonic oscillator with n excitations, essentially. And, throughout this, we found, some unexpected results. I want to just end with one very amazing fact that Plato discovered. I'm still trying to understand this. We found an accidental symmetry of TC interactions, this Tavis-Cumming interaction, and when I say V, it's really mean Plato. So Plato looked at the matrix elements of the Tavis-Cumming interaction, and just by looking to this formula, he discovered a very amazing, which is really fascinating to me, is a symmetry transformation that leaves the matrix elements invariant. This symmetry transformation is very strange because it mixes degrees of freedom in your oscillator with your qubits. It breaks U1 symmetry. It doesn't care about your permutational symmetry. It doesn't care about anything. It's just one weird symmetry. And this has consequences for the problem that we studied. It's not so this consequence of this is that symmetry is that, for example, in this example that appears already on n equal to 3 qubits, whatever unitary transformation that you realize in this two-dimensional subspace corresponding to J prime 1 equal to 1/2 is exactly that unitary is equal to the unitary that you realize in the sector with J equal to 3/2. In this two-dimensional subspace of sector with J equal, they cannot be independent of each other. And as I say, I mean, that's relevant for universality and understanding what type of gates we can realize. Okay? And for a while, that was a total mystery to us. It's still, I would say, a little bit mystery, but at least now we have one explanation, which I think is very fascinating. And the point is we can now explain it using Schwinger's model of angular momentum. Obviously, I don't have enough time to go through it, but Schwinger introduces this way of representing angular momentum representations with two oscillators. And the point is, when you do this transformation for Tavis-Cummings interaction, you will find that after this transformation, for example, your term J plus A goes to B1 dagger B2A, where B1 and B2 are just hypothetical or this Schwinger's essentially oscillators. They are virtual oscillators. They are not real oscillators. And then the point is, this term B1 dagger B2A is invariant under swap of one of these virtual Schwinger oscillators and our actual, oscillators in, for example, our trap line. So it's invariant under swapping them. And this has consequences, and it implies some restrictions, and this symmetry that Plato discovered is actually an implication of that. I think my time is over, so I should stop here. Sorry for going over time, and so this is a summary of the talk, and thank you for your attention.
We have time for just a couple more questions.
Go ahead.
Thanks for the talk.
Sure.
So I want to ask the first part. You mentioned the main application will be verification of fundamental interaction or some quantum simulations. I guess this is still under the assumption that your true system really follows the symmetry itself.
Yes. If I am simulating, for example, let's say a system that has the symmetry, the point is I can take advantage of. And that's the message that I was trying to convey, through this. Symmetry imposes some unexpected restrictions, some no-go theorems that doesn't follow immediately from, but they also brings this useful thing. So let's try to take advantage of it.
So in case if it is like some deviation from a perfectly symmetric system, do you think this is still will be?
Yeah, we can tolerate certain error, and especially because we are calculating determinants in these different sectors. Determinant is to some extent robust against some amount of error, but of course, there's a noise level that breaks this fully. Thank you. Go ahead.
Can you also think, so this was a global U1 symmetry. Can you also think of local symmetries, for instance, in the case of like stabilizers also impose some kind of symmetry?
Yeah, that's a good question.
So in the logical degrees of freedom, you could also argue like there are certain gates that you can have and can't have.
Yes, yes. Of course, when you have encoding logical, you can just, we build in symmetries and we can use it for error detection already. Just, when we encode, we can already use that. But this type of more complicated things, I expect that we can also use it, but I haven't explored. Maybe.
Last question. Yeah.
So question for the first part, I was curious, is it possible, how difficult is it to generalize the qubit multi-body interaction, let's say to qubit, or, continuous variable system?
For the last part?
For the first part, you're detecting, free body.
Yeah, that's certainly works. You can generalize this for qubit definitely. Oscillators, harmonic oscillators, I haven't thought about it, but I expect, at the Lie algebraic level, the reason that why these constraints appear is easy to understand, and they should appear also in the harmonic, the case of harmonic oscillators. Then there's this additional layer that you want to go from Lie algebra to Lie group so that you can do your experiment and detect, what. So because in experiment you have a unitary transformation and you want to measure properties of that. So that's an additional layer that there might be some complications, but it should be doable.
And just a quick follow-up. The second part, you said the interaction has some symmetry, but I was curious, lots of the transformation on continuous groups, for example, SU2 and all that. Do you think it will be more natural to realize some of the symmetry transformations in continuous group with this bosonic systems or this coupled qubit to bosonic systems because you have native continuous diffusion freedom?
So I'm not sure if I understand your question, but James Cumming or Tavis Cumming has a U1 symmetry, which is continuous, and then it has this permutational symmetry. So we take advantage of that U1 symmetry. In fact, I claimed we look at the problem with Hamiltonian X field, Z field, and James Cumming. The point is, having X field makes the problem much, much more complicated because suddenly you cannot avoid the fact that your Hilbert space is infinite dimensional. We usually turn off X field. We never try to avoid it. We try to use it very carefully. We usually turn on X field. Then our space decomposes to finite dimensional, the direct sum of finite dimensional subspaces, and then we know how to do work in that space. So we only turn on X field when the oscillator goes back to its harmonic to its ground state and is decoupled from the qubits. Then we turn on it safely and then do our job and then again we couple them. Sure.
Okay, so we'll take a break and come back at 11:15. So let's thank Iman one more time.
Thank you.